we're going to ask ourselves today, Cristiano, is uh, what if the normal force doesn't equal mg? What if something's pushing down or lifting up while we're trying to slide an object? So you heard me say friction is what times what, and you may even have memorized mu times the normal force, and that's great. But what we're saying now is sometimes the normal force is not mg. In fact, here's our first little example. It says this. Consider the bench below. You know what? Let's make it those benches at the back of the gym that you see, those wooden benches that are against the back wall. Sometimes you have to slide them around, which is being pushed by student number 1. You know what? Just to add some context, let's do that. Is that what you wrote? Okay. So it's being pushed by Cristiano at a rough surface at a constant speed. And you know what? This is something that we should underline. Constant speed. What does constant speed tell me? What's my acceleration exactly as a number, Anthony? Good. Which means the forces must be, I'm looking for where that starts with letter B. Yeah. Okay. But then suddenly student number 2, Baptiste, pushes down on the bench. You know what? He comes and sits on the bench because you know he would if you were pushing it along. He would come along and sit on it while you were pushing it. Okay? If you maintain the same original force as before, what happens to A, the weight of the bench, B, the normal force on the bench, C, the force of friction, and D, the motion of the bench? You know what this is a good job for? A free body diagram. In fact, I did a free body diagram for the first situation. In the first situation, we'll call the force that you're applying F applied. F applied and friction would have to match. In fact, I couldn't quite get it to match when I was typing this. If you want to, you can extend the tail of friction just a tiny bit so it's the same length as F applied. Eyeball it. These are tougher to make in Word than you realize. Okay. But now along comes Baptiste, who sits on it. All right. Cristiano, what are the forces acting on this bench? Get the obvious one. Would it change from here? Would gravity change? No. So I'll make it, eyeball it, the same length as it was in the previous diagram. I want to write that down. Okay. Is the bench sinking into the ground like quicksand? Is it flying to like Superman? So what must be pointing up? Bigger, smaller, or the same size as MG? I'm going to give you a hint. It's not the same size. As soon as you see extra vertical arrows in your diagram, you can be certain that the normal force isn't the same size. So did the normal force have to get bigger or smaller to counteract Baptiste sitting on the bench? Yeah. Exaggerate it so it's stupid obvious. If we want it to be fussy, if you have a teacher in the future who wants them to scale, what you would do is you would take the arrow of the extra push and the arrow of the MG, add them together lengthwise in your head, and draw an arrow pointing up the same length. I'm not that fussy. I want to just make it stupid obvious. What else? Which force are we missing? Is friction going to be bigger, smaller, or the same as in the first situation? Why bigger? I got to be fussy, not more weight. I got to be fussy, not more mass, because weight, that arrow didn't change at all. Which arrow changed? And friction is what times what? Mu times the normal force changed, and so friction is going to be bigger. Let's exaggerate it and label that friction. And so now I can answer this question. I'll do part A right here. What happened to the weight? Now remember, weight is mg, which is why Colton, when you said the weight got bigger, I kind of jumped on you. Did the mass of the bench change? Did gravity change? So weight stayed the same. This is important. Ooh, but Carson, what happened to the normal force? F N, and I'll do an arrow pointing up. There's my increased abbreviation. Why did it get bigger? Because there was more force pushing down on the ground, and the ground didn't let you sink in. But the only way it cannot let you sink in is it has to counteract Baptiste's extra force. That's the extra push, whatever it is. I made up Baptiste sitting on the bench. Could be somebody pushing on the bench or whatever. Okay. Well, then, Callum, if the normal force got bigger, what happened to the force of friction? Bigger, smaller? Why? Because friction is what times what? It's not, no, friction is what times what? You got it on your formula sheet, which you have in front of you and out, like I've said several times. What is friction? Friction is mu times the normal force. Well, if the normal force got bigger, Cristiano, then what got bigger? If this got bigger, then what else got bigger? Yeah. So friction increased. That's why this arrow got bigger. So now it asks about the motion of the bench. Looking at this free body diagram, Cristiano, which way must we be accelerating? Which way is there a bigger unbalanced force? Can you give me a word that starts with the letter L and then has an E? Okay, left or backwards. Now we're moving to the right, but we're accelerating to the left. So what would that look like? How would you describe moving to the right but accelerating to the left? Yeah. In fact, what's going to happen really quickly, we're going to slow down and then we'll probably stop if we're doing that. Now, if it was a smaller force, maybe somebody just threw a couple of big jackets on, you'd still slow down, but not as fast. If it was a bigger force, someone sitting on it, you might slow down within half a second and come to a stop within half a second. Or you would have to push harder. But this question clearly said you kept the same constant applied force, so we couldn't make the applied force bigger. Okay? Lorenzo, does that make sense? Okay, how we walk through that? It says, explain your answer using principles of physics. I think we kind of just did up there. We used Newton's first quite a bit, a little bit of Newton's third to figure out that the normal forces come in pairs, got bigger to prevent you from sinking into the ground. Okay? I'm going to make an executive decision here. This is cool, but I'm going to revisit it in Physics 12. I'm going to revisit it in Physics 12. I'm going to revisit it in Physics 12. So we're going to revisit it in Physics 12, and we're going to jump to example 4. Now, while you're turning the page, technically there's actually two different mu's, two different coefficients of friction. When an object is at rest, mu is a bit bigger. When the object gets moving, mu gets smaller. That's why if you ever tried to slide something really heavy, getting it moving is tough, but once you get it sliding, you can ease up a little bit. You don't have to push quite as hard. If you ever start moving furniture, and most of you in college, when people start moving, when your friends start moving in and out, when you start moving in and out of your houses, you'll do the whole, I'll help my friend move, they'll help me move, you'll get experience in moving furniture, and especially if you're sliding something across the floor, you'll clue in, oh, getting it going is tough. Keeping it sliding, not so tough. But we're not going to talk about that. We're going to skip that. We're going to go straight to example 4. So it says, and you can even scribble this out right here, where it says this is technically mu static. It says, find the maximum force of friction between the mass and the ground for the following objects. Okay. This is a job for a free body diagram. I'm going to zoom in on diagram A. What are the forces acting on it? Get the obvious one, Lorenzo. Caught you zoning out. That's why I'm bringing you back. So, good. Which way? Good. Is it sinking into the ground like quicksand? Are we flying here like Suitman? And I'm going to add another question now. Are there any extra arrows pointing up or down? Okay, unlike this one, and unlike this one, those are going to be different. So because of that, we can say the normal force is going to be the same size as mg. Now, this is asking us to find the maximum force of friction. How do I calculate friction, Lorenzo, from my formula sheet? Friction equals what times what? Look carefully on your formula sheet. Friction equals what times what? Good. That will always be the equation for the force of friction. But what's going to change is the normal force. I don't know the normal force. Oh, but look, 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 look. I don't know the force the same size as the normal force. Which one? Which force is the same size as the normal force? So we can say for this particular situation, it's going to be mu mg. Okay? Lorenzo, what's mu? I don't know. What's mu with you? Oh, they drew it in the picture. How big is the coefficient of friction? How sticky is this surface? What's m? What's g? What's the biggest friction can be? Crunch it, please. Give me all the sig figs. 27.44. Now here's what that means. Don't write this down, look up. Just watch. Suppose you pull this way, don't add that arrow yourself, with 10 newtons, and it doesn't move. How big must friction be in that direction? Not 27.4, 10. What if you pull this way with 25 newtons? How big is friction pointing this way? 25. How hard do you need to pull to get this to start to move in the first place? If you want to get this to start to accelerate, how hard do you need to pull? How hard do you need to pull? So here it says to get A accelerating to the right, you would need to pull with more than what? I'll even add the extra sig fig. If you pull with 27.45 newtons, it'll start to accelerate. Okay. I said to you today we were going to start to look at situations where the normal force was not mg. Here's one. Here's one. Graydon, do you notice there's an extra vertical arrow labeled 55 newtons? Which way is it pushing? Okay, let's remember that. What are the forces acting on this object, Graydon? Get the obvious one. Which way? Is it sinking into the ground like quicksand? Is it flying here like Superman? So their forces have to be balanced vertically. There is a normal force pointing up. Is it going to be bigger, smaller, or the same size as mg? Why bigger? Because not only is it having to cancel out gravity, it's having to cancel out that 55. Make it stupid obvious, folks, so that you notice there's something weird. Okay. It wants us to find the maximum force of friction. Well, Graydon, friction is still mu times the normal force. And I don't know the normal force, but unlike Lorenzo, where you and I were just able to say we knew it was the same size as mg, here we're going to have to do a little thinking. We're going to have to say, we'll write it in the margin here, everything down is going to equal everything up. That's what's happening if you're not sinking into the ground. What's everything down? Well, there's two things, the mg and the 55 has to equal. What's everything up? Do you know how big the normal force is in this situation? mg plus 55. How big is the normal force in this situation? mg plus 55. And you could crunch that right now if you wanted to. I'm lazy. I'm going to do this in one step. I'm going to be lazy but organized because, Graydon, what's mu? I don't know. What's mu with you? And then in brackets, do you know what the normal force is? It's mg plus 55. That's the normal force. So let's all get out our calculators. This is if you want to do this in one step. By the way, I have no problem if you crunch the normal force as a number and just drop it in there. But Callum, I'm naturally lazy and organized. I would go 0.35 times bracket M8 G times 9.8 and then plus 55. By the way, pushing down on an object, does that make it easier to slide or harder to slide? Are you expecting friction to be bigger than 27.44 or smaller than 27.44? Bigger, 46.69. That's the biggest friction can be. Now, that doesn't mean that friction, Cristiano, is that okay? Did you remember to put it in brackets? You have to go 0.35 times bracket 8 times 9.8 plus 55 close bracket because that's the whole normal force. Or what you could have done, Cristiano, is you could have gone 8 times 9.8 plus 55 on your calculator and then said, okay, it's going to be mu times the normal times the normal force. You also get the 46.69. You're still looking lost. Okay, don't clear your calculator. Let me pause the video. Don't write this down, look up. If I pull this way with 30 newtons, what would happen? How big would friction be in this direction? And nothing will happen. What if I pull with, what if I pull with 45 newtons? Now, you would probably be able to tell that it was just about ready to slide. You could feel, okay, this thing is ready to go. What if I pull with 46.7 newtons? Now it will accelerate because we're bigger than the biggest friction can be. So in the bottom of the page, let's erase all this because we didn't make that part of our free body diagram. It says you would need to pull with more than what? 46.69 newtons. That doesn't mean that friction is always that big. Friction is as big as it needs to be. It's a Newton's third law reactive force, so it'll match what you're doing until it can't match you anymore. Then things will start to accelerate. Ooh, Tita, let's try this last one here together, you and I. This time it looks like we're lifting up with 55 newtons. By the way, lifting up, do you think that's going to make the normal force bigger or smaller? It's going to make it smaller. Let's do a free body diagram. What are the forces acting on it? Get the obvious one. Good. There's going to be a normal force. Is there an extra vertical arrow in this situation? An extra vertical force? So it's not going to be mg. Lifting up, the normal force is going to be smaller than gravity. I'll make it a little bit to make it obvious. Now, it wants us to find friction. Friction is still going to be mu times the normal force. I don't know the normal force. I'm going to have to figure this out. Are we sinking to the ground like quicksand? Are we flying into the air like Superman? What that means is everything down equals everything. So what's everything down? I'll change colors. mg has to equal, what's everything up? Two things. The normal force and the 55. How would I get the normal force by itself? How would I move the 55 over? Minus it. Yep. The mg will drop down like a domino. There'll be a minus 55. That equals the normal force. And again, Cristiano, if you wanted to, you could go 8 times 9.8 minus 55 equals, and then go mu times that. Or if you want to do it in one step, I'll write it in one step. If you want to do it in one step, it's going to be, Tita, what's mu? I don't know, what's mu with you? Still 0.35, yes? And then the normal force is going to be in brackets, mg minus 55, close bracket. In fact, you might be able to just backspace and edit and change the plus sign to a minus sign if you haven't typed a whole bunch of extra stuff. I've typed extra stuff, so I've got to start over. Bracket m8 times 9.8 minus 55. And now I get the biggest friction can be in this case is 8.19 newtons. So to get this mass accelerating to the right, theta, we would need to pull with more than what? 8.19. Yeah. Pull with 8.20, it's going to accelerate. Pull with 8.18, nope. So what you're going to have to start doing going forward is just be cautious, especially in today's lesson. The normal force will rarely equal mg. How much more time have I got? We'll probably finish with example 5 here, and then we'll continue next class. Says for each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, find the acceleration. You know what? I think we can just draw a line down the middle of the page, and we'll do these simultaneously. That's the fancy phrase for at the same time. I think before we start, though, you know what we should probably do before we dive on in? What might this be a good job for? A free body diagram. Okay, so Napat, it looks like we have identical situations, but in the second situation, we're pushing down. What are the forces on the first 10 kilogram block? Get the obvious one. Good. What else? Bigger, smaller, or the same size as mg? Good. And then this 20, I'll call that F applied, and I'll just make sure that I did notice it. Do they want me to include friction? Yes. How do I know? Because in the diagram, they included a coefficient of friction. That's their way of saying you better take that into account. Which way will friction be pointing? And I think it's going to be smaller than F applied. What about in the second diagram? What are the forces acting on it? Get the good. What else? Bigger, smaller, or the same size as mg? Bigger. I'll exaggerate it so it catches my eye. Then we still have the 20, which is F applied. We also still have friction. Now, friction's going to be bigger. I got to be honest, it might be bigger than the 20. If it's bigger than the 20, if friction ends up being 23 newtons, this ain't going anywhere. Then A is 0. But let's find it. Okay. Anthony, what does A say they want me to do? Okay, let's do that. Let's do a part A. We'll do these simultaneously. What they really mean is if you look at the first diagram, are we sinking into the ground like quicksand? Are we flying here like Superman? Then vertically everything down equals everything. What is everything up? What's the only arrow pointing up? What's the only arrow pointing down? There's my vertical force equation. For part B, are we sinking into the ground like quicksand? No. Are we flying here like Superman? No. So still, everything down is going to equal everything. But it's a bit trickier. What's everything up? One arrow. Good. What's everything down? And there's another arrow pointing down. There's another arrow pointing down. How big? You know what? mg plus 15. There's my vertical equation. Yeah, normal force is bigger because the normal is mg. Now you're adding something to it. Yep. Ashton, what does B want me to find? Uh-oh, someone's been zoning out. Find the force of friction is what times what? So it's going to be mu Fn, and over here, friction is also going to be mu Fn. Oh, this is convenient because, Anthony, what did you tell me the normal force was the same size as in part A for the first diagram? So I can go mu mg. What about for the second diagram? Well, here, Anthony, it's going to be mu, but what did you tell me the normal force was the same as? I think you're right, but I couldn't hear you. And that's going to be in brackets. What's mu? I don't know. What's mu? 0.12 M 10 G 9.8. Anthony, what do you get? I can do this in my head. Can I? Sure, I can. It's going to be 98 times 1.2. I can do that. It's going to be 9.8 plus 1.96, 10.8, 11.76, Anthony? No, yes? 0.12 times 10 times 9.8? 11.76? Okay. That's going to be newtons, because it's a force. What about for the second diagram? Here, friction is going to be, what's mu? 0.12 times, in brackets, 10 times 9.8 plus 15. Do that one in your head, Mr. Dueck? Well, maybe. 10 times 9.8 is 98 plus 15. Oh, maybe this will work. It'll be 108, be 113. 113 times 0.12. How would I do that, Carson? I would go 11.3 plus 2.26, 11.3, 13.56. Yeah. Is that okay? Caden, what does part C say they want me to do? Okay, in this first diagram, who's probably winning? Who's probably losing? What's my equation? Winner minus loser equals MA. In the second situation, who's probably winning? I think F applied. Who's probably losing? Mr. Dueck, I have the same equation for both. Does that mean I'll get the same answer for both? No. Different parameters. Friction's going to be different. How will we know we've guessed wrong if we solve for A and A ends up being what? Remember? Negative. So we can find that out. Okay. Sophia, what does D want me to find? Oh, how would I get the A by itself? Colton's theorem. A is going to be F applied minus friction all over M. What about on the right-hand side? How would I get the A by itself? In fact, yeah. Now, again, you might say, won't I get the same answer? No, the values that we're going to put in will be different, but I hope you're starting to see this is getting kind of repetitive. There's only so many combinations I can give you where it's going to come down to good free body diagram, who's winning, who's losing. I've scrolled down a little bit, Sophia. You're going to have to give me the numbers. What was the applied force? Was it 20? Minus what was friction? 11. What was the mass? What do you get? Oh, I can do this in my head. Dividing by 10? Even you all can do that. Yeah, let's see. It's going to be 20 take away 11. It's going to be 9 take away 0.76. It's going to be 8.23. Is it 0.823, I think? 0.824. 4. There's a 6. 0.824. Yes? Wow, I made a dumb mistake. If you're doing your calculator, what, brackets around the top, right? Or fraction button. Sophia, what about the right-hand side? It's going to be still 20, but what was friction this time? 13 point something, wasn't it? 0.56 divided by 10. Yeah, I can do this in my head. 20 take away 13 is 7, take away 0.56 is 6.44, divided by 10, 0.644, right? Gotta be that. Am I right? You check me with the calculator? Sounds good. So I can handle if they give me an extra vertical force column. I just need to see it and then adjust the normal force accordingly. How will I adjust the normal force, Anthony? Everything down is going to equal everything. Yeah, unless it is sinking into the ground like quicksand, and I'm not going to give you one like that. Unless it is flying through like soup, and I'm not going to give you one like that. We're going to pause here. Most of you still have not finished lesson 5. Most of you are still going to be wrestling with some questions from lesson 5. There was some questions in lesson 5 involving dragsters and rollerblades. I'm going to visit them. I'm actually going to do them on Friday. So if you're still stuck, you can do most of the questions from lesson 5 and probably still pause. We'll finish this off next class. But first, short video. Put your pencils down, look up.